Right. Question 9. Firstly, show that this result is true. So this just wants you to multiply it out. This is just some, oh, that's supposed to be an alpha. Just some fairly unpleasant, long-winded algebra. We're going to carefully multiply out the whole thing. It's up to you how much you want to write out middle stages here. I'm just going to multiply this straight through. So multiplying the second bracket by the first term gives me an alpha squared beta squared. That would give me an alpha beta squared gamma. And then that times that would give me an alpha squared beta gamma. Then multiplying by the middle term, we've got an alpha beta squared gamma plus beta squared gamma squared plus alpha beta gamma squared, that's that one times that one. And the last one, multiplying through alpha squared beta gamma plus alpha beta gamma squared plus alpha squared gamma squared alpha squared. That's got it all multiplied out. If we collect together like terms from in that, we've got these bits first, haven't we? We've got the alpha squared beta squared, we've got the beta squared gamma squared, and we've got the gamma squared alpha squared. That's that one taken out. We've then got alpha beta squared gamma is there, and it's also there underneath it. So we've got two lots of alpha beta squared gamma. We've got two lots of alpha squared beta gamma. There's one, and where is it? There's the other one. And we've got two lots of the other one that we're missing, alpha beta gamma squared. Alpha beta gamma squared, there and there. So we've got that. And now it's almost the James Hens trick, where we know where we're supposed to be heading with this. And we can almost say hence equals that. We've got a common factor here of 2 alpha beta gamma. The first term we need to multiply by beta, that one we need to multiply by alpha, and that one we need to multiply by gamma. So let's just write it like that, and then that's what we're supposed to get. So that's quite nice. That's got the first part sorted. Then, now this is where it gets really interesting. It's given that alpha, beta and gamma are roots of the cubic equation x cubed plus px squared minus 4x plus 3, where p is a constant. Write, or find the value of 1 over alpha squared, 1 over beta squared, 1 over gamma squared. Now we could try and do something with the substitution here to find the quadratic that has roots 1 over alpha squared, 1 over beta squared, 1 over gamma squared, and work our way through that. But there must be some kind of a connection between those two things. That's the thing that we're thinking. So let's start by seeing if we can spot where the connection is before we do anything else. And even if we just play around with this a little bit and see if we get anywhere, it might be worth doing it. So we're going to start with that 1 over alpha squared plus 1 over beta squared plus 1 over gamma squared. Not entirely sure where I'm going with this, but we've got 3 fractions added together, and our instinct there is to put them over a common denominator. So the common denominator is alpha squared, beta squared, gamma squared. The first fraction, to put it over that denominator, we need to multiply that by, well, we would have beta squared. If we multiplied it by alpha squared, beta squared, gamma squared, it would give us that. Is that right? That's the first bit, yes. And the second fraction, we would get alpha squared, gamma squared on the top. And the third fraction, we would get alpha squared, beta squared on the top. Now it's starting to look a little bit like where we came from originally, because we have that bit there is this. And we want to try and get back to things in terms of just alpha, beta and gamma. And if you look at how it originally started, there you've got that bit that we've now got as our top of our fraction. And the rest of this expression don't involve squared bits, they just involve alpha, beta and gamma. So let's imagine that rearranged. If you make that the subject, you make that bit the subject, then you'd have that expression, the squared bit, take away this expression here. So let's see where that takes us. If we now write it as being the alpha plus beta plus gamma squared. Sorry, it's not that bit, is it? It's alpha beta plus beta gamma. I can't see it all on the same screen. It's that bit squared. Take away the two alpha beta gamma, alpha plus beta plus gamma, all over alpha squared, beta squared, gamma squared. Now that it doesn't feel like we've got an awful long way yet, but we've turned this into something that is all to do with the roots of the original equation that we've just been given. So if we go back to that equation now, the equation was x cubed plus px squared minus 4x plus 3 is 0. And from that equation we can say that alpha beta gamma is equal to, well, what would alpha beta gamma be equal to? Minus 3. Minus 3 over 1, so minus 3. We could also say that alpha beta plus beta gamma plus gamma alpha is equal to minus 4. That's minus 4 over 1. And alpha plus beta plus gamma is equal to minus p. Okay, so we've got those things. So now we've got to try and fit that bit of information to what we've got here. And so we've got 1 over alpha squared plus 1 over beta squared plus 1 over gamma squared, which is just that expression there, is that bit all squared, minus 4 squared, minus twice alpha beta gamma, twice minus 3, times alpha plus beta plus gamma, which is minus p, divided by alpha squared, beta squared, gamma squared, which is what you get if you square that bit. So divided by minus 3 squared, so we have 16, and then we've got, I think, minus 6p, and we're divided by 9, and that will be the answer. There it is. Great, and that's maths.